4.5 billion years ago, Earth did not resemble a world. It resembled an accident. There were no skies in the way we understand skies. No blue horizon, no clouds drifting gently across sunlight, no oceans breathing against shorelines. The planet existed as a violent sphere of molten rock, a rotating furnace suspended inside a chaotic solar system that had not yet finished forming. If you could stand there, which you could not, the ground beneath you would not be solid ground at all. It would glow. Entire landscapes moved like slow rivers made of fire. Mountains tried to form and immediately collapsed back into magma. Every direction shimmered orange and white, brighter than any desert noon. The heat would not merely burn skin, it would vaporize matter. Earth had just been born from countless collisions of rock and metal fragments orbiting the young Sunday. These fragments, called planetesimals, slammed into each other at unimaginable speeds. Each impact released more energy than modern nuclear arsenals combined. Every collision melted more of the growing planet. Instead of cooling after formation, Earth stayed liquid because formation never really stopped. And then something even worse happened. A protoplanet roughly the size of Mars struck the young Earth. Scientists call this body Theia. The collision did not crack Earth, it liquefied it again. Whole regions were ejected into space. From that debris, the Moon would later form, but at the time it meant one thing: Earth reset to fire once more. The crust, if it tried to exist, was erased. So the early Earth was not simply hot, it was continuously remelted. The sky above this world did not contain oxygen. There was nothing breathable, nothing calm, nothing stable. Instead, volcanic gases flooded upward without limit: carbon dioxide, sulfur dioxide, methane, ammonia, nitrogen, and enormous amounts of water vapor. Not water yet, vapor, because liquid water could not survive here. At these temperatures, oceans could not form. Any droplet instantly boiled. Any condensation flashed back into steam before touching the surface. The entire planet was wrapped in a dense, opaque, atmospheric blanket, thousands of times thicker than modern air. Light from the sun barely reached the molten surface. Earth glowed from its own heat more than from sunlight. It was, effectively, a planet-sized pressure cooker. Yet hidden inside that suffocating atmosphere was the most important ingredient for everything that would ever live: water. Not delivered as gentle rain, not stored in seas, but trapped as superheated vapor rising endlessly from volcanoes across the planet. Volcanoes were not isolated mountains then, they were the planet's skin. Everywhere magma met the surface, gases escaped violently upward. Entire hemispheres erupted at once. The ground opened and resealed constantly. Earth did not have continents yet. It had convection currents, massive circulations of molten rock slowly overturning the planet's outer layer. And above this churning surface, the atmosphere thickened. Water vapor accumulated for millions of years. Imagine clouds that never end. Clouds deeper than modern oceans. Clouds so dense they form a permanent global ceiling. No blue gaps, no sunlight shafts, just a dark reddish haze lit occasionally by constant lightning storms created by thermal turbulence in the superheated air. But still no rain, because rain needs cooling. At this stage, Earth remained too hot for water to fall and remain liquid. Instead, something strange occurred. Water tried to rain, fell as droplets, and evaporated before reaching the ground. This happened endlessly, a cycle without success. A planet attempting precipitation but failing every single time. It was the beginning of the longest storm in planetary history, before the storm even truly started. Meanwhile, deep inside the planet, heavier metals sank toward the core. Iron and nickel migrated downward, releasing gravitational energy that kept the mantle hot. The formation of the core itself acted like a giant internal heater. Earth was not only heated from impacts and volcanoes, it heated itself from within. Cooling a world like this takes time. Millions of years passed, then tens of millions. Gradually, very gradually, the outermost layer of magma began to lose heat to space. A thin crust tried to form fragile, temporary, constantly destroyed by impacts from leftover debris still orbiting the Sunday asteroids, struck relentlessly. Each collision punched through the cooling skin and exposed molten interior again. This era is known as the Late Heavy Bombardment. From orbit, Earth would have looked like a glowing ember being sandblasted by cosmic gravel. Every impact injected more vapor into the atmosphere. Many incoming objects carried ice-frozen water from outer regions of the solar system. When they struck, that ice flashed into steam and joined the growing atmospheric reservoir. So water came from two places, from inside Earth and from space, but still no oceans existed. Instead, the sky grew thicker. Pressure increased beyond anything humans could survive. Standing at the surface again, impossible, the air above would weigh as much as being kilometers underwater today. The horizon would blur behind a dense orange-grey fog. Sound would carry strangely through the heavy atmosphere. Thunder would roll continuously, overlapping with itself, never truly ending. Lightning flickered constantly, not occasional flashes, but a near-permanent electrical storm wrapping the planet. Electrical energy crackled through the gases, breaking molecules apart and reforming them again. Chemistry had begun long before life existed. Earth was slowly preparing itself. Then, for the first time in its existence, the temperature crossed a critical threshold. Not cold, just less impossibly hot. The surface cooled below the boiling point of rock, then below the boiling point of metals, then finally approached the boiling point of water at extreme pressure. The atmosphere remained scorching, but conditions changed enough that condensation could begin to persist slightly longer. Tiny droplets formed in the upper atmosphere and did not instantly vanish. They fell farther than before. They still evaporated, but not as quickly. And that tiny delay changed the fate of the planet. Because once droplets survive longer, more droplets join them. Clouds thicken further. Upper layers cool slightly faster due to reflection of sunlight. The first true weather patterns began to organize. Convection towers rose kilometers high. The atmosphere started separating into layers, a primitive troposphere emerging. Earth was approaching the moment when the sky would finally fall. Not as a shower, not as a storm, but as a planetary collapse of water from sky to ground. The first raindrops that would reach the surface were already forming countless kilometers above a glowing, fractured crust waiting below. And when they finally touched the planet, they would not end the heat. They would fight it, and they would lose at first, but they would keep coming. At first, the rain did not sound like rain. There was no gentle tapping, no rhythm against leaves or soil, because neither leaves nor soil existed. When the earliest true droplets finally survived their fall and struck the surface, they landed on glowing rock hotter than a furnace wall. The result was not a splash, it was an explosion. Each drop flashed instantly into steam. The moment water touched the ground, it vanished in a violent hiss, expanding hundreds of times in volume. Billions upon billions of impacts happened every second across the planet, producing a constant roaring sound, a planet-wide scream of vaporization. If hearing could survive in such pressure and heat, the noise would not come in waves. It would be a continuous wall of sound. The rain had begun, but Earth refused to accept it. Water fell, rock rejected it. Above the surface, thick layers of cloud fed the downpour endlessly. In the upper atmosphere, temperatures were lower than near the molten crust, allowing droplets to grow larger and heavier. Gravity pulled them downward faster than evaporation could destroy them, but the closer they came to the ground, the hotter the environment became. Many evaporated mid-fall, rising again as vapor and returning to the clouds. This created a strange loop rain that almost worked. For millions of years, Earth experienced precipitation that could never accumulate. A global distillation machine operated day and night. Water condensed high above, fell toward the surface, vaporized again, and rose back into the sky. The cycle never paused. The planet's rotation merely shifted where the loudest boiling occurred. There were no dry regions. There were no wet regions. There was only the attempt at wetness. The atmosphere thickened further because vapor kept being recycled instead of stored as oceans. Pressure increased, trapping more heat. The greenhouse effect intensified, holding thermal energy close to the surface. Even though space continuously stole heat away, Earth's own atmosphere fought to keep the planet hot. But the rain persisted. Eventually, a subtle change began. The earliest crust, though unstable, started lasting longer between asteroid impacts. Small plates of hardened basalt formed and survived for centuries, then millennia, then longer. They did not remain smooth. As magma beneath shifted, the surface cracked and folded, creating valleys and basins. Tiny depressions appeared insignificant at first, but they offered something new, slightly cooler locations. In those shallow basins, rain lasted a fraction of a second longer before boiling. Instead of immediate vaporization, droplets pooled briefly into shimmering films. The films bubbled violently, then disappeared. Yet every time this happened, the rock beneath cooled just a little. Cooling rock required energy, and the energy came from the heat of the rock itself. The rain was stealing heat. Individually, each droplet did nothing. Collectively, they became a planetary cooling system. Steam clouds grew thicker near the surface as boiling intensified. From above, Earth would have looked wrapped in layered fog, darker cloud decks above, bright white steam plumes below. The lower atmosphere churned constantly, circulating heat upward where it could escape to space. The hydrological cycle, though primitive, was now functioning as a thermal engine. Still, The planet remained hostile beyond imagination. Lightning storms increased as temperature differences between atmospheric layers sharpened. Electric arcs stretched across entire horizons, sometimes connecting cloud to cloud rather than cloud to ground. The surface glowed through the fog in dim patches, like embers behind smoke. Meteor impacts continued to puncture the crust, occasionally remelting regions and resetting local cooling. Yet something irreversible had begun. Earth could now lose heat faster than it gained it. Over millions of years, average surface temperatures slowly dropped. Not to comfort, not even close, but below the point where every drop instantly vanished. Some water began surviving for seconds instead of moments. Seconds turned into minutes. In deeper depressions formed by tectonic stretching, rainwater briefly collected into shallow boiling puddles. They churned like cauldrons, constantly releasing steam upward. The puddles never lasted long, but they returned repeatedly in the same locations because geography now mattered. The planet had started shaping its future oceans without knowing it. At this stage, the sun itself appeared dimmer than today. Early in its life, our star emitted slightly less energy. Paradoxically, that faintness helped the rain. Less solar input meant the atmosphere could eventually cool despite greenhouse gases. Without that, Earth might have stayed a permanent steam world. As cooling progressed, cloud layers thickened even more, reflecting sunlight back into space. The sky grew darker from the surface perspective, not because night had come, but because sunlight could not penetrate the endless storm canopy. The planet lived under permanent twilight, lit by lightning and lava, and then came the first true cooling event. In a large tectonic basin, rain fell continuously for centuries without a major impact resetting it. Water accumulated faster than it evaporated. The pool remained boiling violently, but present. Waves of steam rose kilometers high, yet beneath them, liquid persisted. For the first time in Earth's history, water touched rock and stayed there. The significance was enormous. Liquid water absorbs heat far more effectively than vapor. Once stable pools formed, they accelerated cooling locally. Surrounding crust hardened further. Adjacent basins repeated the process. Instead of isolated flashes of puddles, entire regions began hosting temporary lakes of scalding water. They were not oceans yet. They were battlefields. Rock tried to remain molten. Water tried to exist. Each drop removed a tiny fraction of heat from the crust. Over thousands of years, millions of years, the balance shifted slowly but decisively. The sound of the planet changed. What was once a constant explosive hiss gradually softened into a deeper rumble of boiling reservoirs. Steam vents roared upward like geysers across entire landscapes. Thick fog blanketed the ground. The atmosphere smelled, if smelling were possible, strongly of sulfur and minerals leached from fresh rock by hot water reactions. Chemistry intensified everywhere, water lingered. Minerals dissolved into solution, turning the primitive lakes dark and metallic. Iron, silica, magnesium, and countless ions filled the liquid. Each storm washed new material into the pools. The rain was no longer just cooling the planet, it was preparing the ingredients of a future ocean. Yet Earth was still unrecognizable. No horizon lines, only vapor curtains. No sky, only layered darkness. No calm moment, only continuous precipitation, and the rain did not weaken. If anything, it strengthened. As more vapor condensed instead of remaining airborne, latent heat released in clouds powered larger storm systems. Planet-wide cyclonic circulation developed. Winds screamed around the globe, unobstructed by mountains, because mountains did not truly exist yet. The entire surface was low and unstable, a shifting basaltic plain. Rain fell diagonally under hurricane-force winds, sometimes nearly horizontal. Droplets merged into sheets, sheets into torrents. Some regions experienced what could only be described as atmospheric rivers, continuous waterfalls descending from the sky for centuries at a time. Still, despite all this, oceans had not fully formed. They were coming, because eventually the crust would cool just enough for the rain to win permanently. The victory of water did not happen in a single moment. There was no day when the rain suddenly stopped boiling and the oceans quietly appeared. Instead, the change came through a tipping point, the kind of planetary shift that once crossed could never reverse again. For millions of years, the rain and the rock had been locked in balance. Water cooled the crust, while heat from below reheated it. But the interior of Earth was also evolving. Deep inside the mantle, convection currents slowly carried hotter material upward and cooler material downward. Each cycle transported heat toward the surface where space could steal it away. Cooling from above and cooling from below were finally working together. The crust thickened. Instead of thin floating plates constantly melting, large regions began surviving for thousands of years without remelting. Cracks no longer instantly filled with magma. Lava flows still existed, but they no longer covered entire hemispheres. The planet's skin was stabilizing, and because it stabilized, water could finally remain long enough to accumulate. In the deepest basins, the boiling slowed. Not stopped, never gentle, but slowed. Pools grew wider than impact craters. Steam clouds rose continuously, yet beneath them, liquid water no longer vanished completely between storms. Every hour of rainfall added slightly more than was lost. Earth had entered a new regime. Now, rain did not merely cool the ground. Rain began to reshape the planet. Flowing water carved channels into the young basalt crust. At first, they lasted only decades before being buried by volcanic resurfacing. But resurfacing was happening less often now. Channels persisted, guiding more water into the same depressions again and again. Networks formed primitive drainage systems across a world still under constant storm. The sky above remained dark and oppressive. Clouds spanned the entire planet, stacked in layers tens of kilometers thick. Sunlight almost never reached the surface directly. Instead, the world lived in dim red twilight, illuminated by lightning and reflections from glowing volcanic fields. Thunder never ended. It rolled endlessly across the atmosphere, echoing through dense air that carried sound far beyond modern distances. A single lightning strike could stretch hundreds of kilometers, branching across the cloud ceiling. Each strike injected energy into the atmosphere, breaking apart molecules and forming new chemical combinations. Meanwhile, the rain intensified, because now something new happened: evaporation decreased. As more water remained on the surface, less returned immediately to the sky. Atmospheric vapor slowly declined relative to liquid reservoirs. Pressure began falling from its earlier extreme levels. The greenhouse blanket thinned slightly, and that allowed temperatures to drop further. Cooling accelerated. In geological terms, this moment was catastrophic, but in the opposite direction of destruction. Earth was calming. The feedback loop that once trapped heat now worked to remove it. Every new pool of water became a heat sink. Every new basin collected storms that could not fully escape back into the sky. The first proto-ocean appeared, not recognizable yet, not blue, not calm. It was a global network of connected boiling seas stretching across low regions of the planet. Waves crashed under hurricane winds, while steam columns rose continuously like thousands of volcanoes made of water instead of lava. But this time, when rain fell into those waters, it stayed water. From orbit, the change would have been dramatic. Instead of a glowing surface beneath haze, darker regions emerged, massive reflective patches where liquid dominated over rock. The planet's brightness shifted. Clouds above these areas grew denser as evaporation still occurred. Yet the balance had tipped irreversibly. Water had conquered gravity's basin. Over the next tens of millions of years, these seas deepened. Impacts still struck occasionally, sending tsunamis across the young oceans and briefly reboiling sections into vapor. Yet the water always returned. There was now too much to erase. Minerals poured into the oceans from every rainfall. Each drop dissolved microscopic particles from fresh volcanic rock and carried them downhill. Rivers, true rivers, now transported sediments continuously. The water darkened with dissolved metals and silicates, forming a chemical broth unlike anything seen today. The ocean was not blue. It was nearly black. Above it, the sky remained heavy and grey-orange. The sun appeared only as a faint, bright disk when clouds thinned momentarily, a rare occurrence. Most of the time, the world existed in dimness, lit by lightning flickering across the storm ceiling. Yet this darkness hid a transformation more important than the oceans themselves. Because once liquid water covered large portions of Earth, temperature differences stabilized. The atmosphere began organizing into recognizable circulation cells. Instead of chaotic global turbulence, patterns emerged: equatorial heating zones and cooler polar regions, even though poles themselves were still warm by modern standards. Weather had evolved from constant chaos into structured chaos. The rain, however, did not end. It continued for millions of years more. Not because Earth refused to cool, but because there was simply so much water in the sky and so much heat still escaping from below. The planet was bleeding energy slowly into space, and precipitation was the mechanism allowing that loss. During this time, coastlines existed only temporarily. Rising magma reshaped them. New crust formed at ridges and sank elsewhere. The oceans expanded and contracted locally, but globally they grew deeper. Eventually, a remarkable silence began appearing between storms. At first it lasted minutes, rare breaks where thunder softened and rainfall weakened to mist. Then hours, then longer. The cloud cover thinned in places. For the first time in Earth's existence, unfiltered sunlight briefly touched liquid water. The surface did not boil. It steamed gently. That gentle steaming marked the end of Earth's most violent era. The planet was no longer a magma world resisting water. It had become a water world moderating fire. The endless storm was beginning to fade, not completely gone, but no longer absolute. Rain still dominated climate, yet now it shared the sky with something new, cycles of clearing. And with those clearings came stability. Temperatures dropped below the continuous boiling point of water across large regions. Oceans persisted permanently. The atmosphere slowly transitioned from a crushing vapor blanket into a true sky, still toxic, still harsh, but structured. Earth finally possessed three distinct domains: solid crust, liquid ocean, gaseous atmosphere. Only then could the next chapter of the planet's story begin, not the formation of water, but what water would do next. Because a world covered in oceans beneath lightning-filled skies was no longer merely cooling. It was preparing chemistry. And chemistry, given enough time, begins to organize itself in unexpected ways. The rain had built the stage. Now something would eventually step onto it. By the time two oceans covered much of the young Earth, the storm had not ended, it had matured. The planet was no longer trying to create water, now it was trying to balance it. The surface temperature had finally fallen below the point where every raindrop exploded instantly into steam. Instead, rain struck the ocean and merged with it. The sound changed completely. What was once a constant roar of vaporization became the deep percussion of colossal rainfall hammering an endless sea. But this was not normal rain. The atmosphere still contained far more water vapor than today. Clouds were thicker than mountains. Entire layers of the sky functioned like reservoirs, holding oceans above oceans in suspension. When condensation occurred, it did not produce showers, it produced planetary downpours. Everywhere on Earth, water fell almost continuously. Imagine standing on a shoreline. If shorelines had been stable enough to stand on, the horizon would not be visible. A grey curtain would stretch from sky to ocean in every direction. Waves taller than buildings rolled beneath hurricane-force winds, and above them torrents descended without pause. There were no seasons yet, no dry climates, no deserts, no calm days. The rain was global. The early sun shone dimmer than today, and thick clouds reflected much of its energy back into space. Without that reflection, the greenhouse atmosphere would have reheated the planet. Instead, the clouds cooled it while also feeding endless precipitation. Earth had entered a self-regulating cycle. Heat escaped upward, while water cycled downward. The sky had become a reservoir, slowly draining into the oceans. But the draining took millions of years. Even though oceans existed, they were shallow compared to what they would become. The atmosphere still held an enormous fraction of the planet's total water inventory. Every storm transferred a tiny portion downward. Over geological time, those tiny portions accumulated into kilometers of depth. Each raindrop was part of a transfer process. Sky, ocean, sky, ocean. Except now, slightly more water stayed below than returned above. And that imbalance reshaped the world. As rain struck exposed rock along volcanic islands, it reacted chemically with fresh basalt. Carbon dioxide dissolved into water, forming weak carbonic acid, which slowly ate into the crust. Minerals released into rivers and washed into the seas. The ocean's chemistry changed constantly, becoming richer in ions. The rain was not pure water. It was a chemical delivery system. Lightning storms intensified this chemistry further. Electrical discharges split atmospheric gases apart, nitrogen bonds broke and reformed, sulfur compounds oxidized, carbon molecules rearranged. Many of these newly formed compounds dissolved into falling rain and entered the ocean. So every storm altered the ocean's composition. The sea became a vast reactive mixture, warmed from below by geothermal heat and stirred violently from above by storms. There were no stable layers, yet convection churned water from surface to depth. Hydrothermal vents on the ocean floor injected superheated mineral-rich fluids upward, while cold rain hammered downward. The planet was mixing itself thoroughly. Meanwhile, continents still barely existed. Only scattered volcanic highlands rose above the ocean surface, constantly reshaped by eruptions. Rain fell hardest on these regions, eroding them almost as fast as they formed. Rivers cut channels within decades, then lava buried them and rain carved them again. No mountain range survived long enough to grow tall. Earth was smoothing itself under rainfall. Over time, the atmospheric pressure slowly declined. As water transferred permanently into oceans, the thickness of the vapor blanket reduced. The sky lightened slightly. Instead of deep orange darkness, a dim grey brightness dominated. The sun appeared as a pale disk more often, though still rarely clear. This subtle brightening affected temperature gradients across the planet. Equatorial regions received slightly more energy than polar ones. Winds strengthened along predictable paths. Global circulation cells emerged, steering storm belts around the planet. For the first time, weather patterns had direction. Massive cyclonic bands wrapped around the equator, feeding continuous rainfall zones. Outside them, slightly calmer regions appeared, though calm still meant powerful storms by modern standards. The hydrological cycle had become organized instead of random, and with organization came efficiency. Rain began transporting heat from equator toward poles through ocean currents. Warm water rose, cooled, sank, and moved again. This circulation stabilized surface conditions further. Instead of localized boiling seas and cooler regions, the planet approached a uniform, warm, oceanic climate. Earth had become a water planet in function, not just appearance. From space, the surface would now reflect a dull, metallic sheen beneath moving cloud systems. Only rare volcanic islands interrupted the expanse. Lightning illuminated storm spirals, visible even from orbit. The moon, now fully formed and closer than today, pulled enormous tides across the global ocean. Tides hundreds of meters high surged across shallow basins, twice each rotation. These tides did more than move water. They churned chemistry. They mixed minerals and heat repeatedly, preventing stagnation. The coastline zones, though temporary, experienced constant flooding and exposure cycles, concentrating dissolved compounds. Even the moon was participating in preparing the oceans, and still the rain continued. Not endlessly intense anymore, but persistent beyond anything modern Earth has ever known. A human lifetime would pass without witnessing a completely dry year. Generations, if life existed yet, would never know a clear sky. The atmosphere was slowly surrendering its water. Every storm transferred another fraction downward, and as the oceans deepened, they began influencing the sky in return. As the oceans deepened, the direction of control began to reverse. For most of Earth's early history, The sky dictated the planet's behavior. Heat rose upward, vapor gathered above, and rain fell as a consequence of atmospheric physics. But once vast bodies of liquid water covered most of the surface, the ocean itself started governing the atmosphere. Water stores heat far better than rock. During the magma era, temperatures changed violently because stone heats and cools quickly. Now, with kilometers of liquid covering the crust, energy no longer spiked and dropped rapidly. The ocean absorbed solar radiation, geothermal warmth from below, and lightning-driven atmospheric heat from above, then released it slowly. The planet's climate stabilized. Storms still dominated, but they were no longer purely chaotic explosions of vapor. Instead, they followed gradients created by ocean temperature differences. Warmer waters produced towering cloud systems. Cooler waters allowed thinner cloud layers. The sky, once uniform, became patterned. For the first time, different regions of Earth experienced slightly different weather. Near the equator, warm oceans fed immense convection towers. Warm air rose continuously, carrying moisture high into the atmosphere, where it condensed into colossal storm complexes. These were not hurricanes as we know them. They were permanent, rotating systems spanning thousands of kilometers, circling the planet endlessly. Closer to the poles, cooler waters produced lower cloud decks and steady rainfall instead of violent deluges. The rain still rarely stopped, but its character changed a heavy, persistent descent rather than explosive torrents. The world now had climate zones, and those zones affected how water moved between sky and sea. Above warm regions, evaporation increased. Massive quantities of vapor lifted upward daily, feeding thick cloud belts. Winds transported that vapor toward cooler regions where it condensed and fell again. Instead of falling randomly, water now migrated across the globe before returning to the ocean. The hydrological cycle had become planetary circulation. Each droplet might rise at the equator, travel thousands of kilometers through the sky, and fall near the poles. Then currents carried it back through the sea toward warmer waters. This continuous movement mixed the oceans chemically and thermally. Earth was running a giant distillation and mixing process simultaneously. The atmosphere responded dramatically to this new oceanic control. Because vapor was no longer trapped evenly across the planet, certain regions cleared slightly more often than others. Brief breaks in the clouds allowed sunlight to penetrate deeper than before. The surface brightness increased gradually over millions of years, still dim but brighter. Those faint shafts of sunlight warmed the upper ocean layers differently from the depths. A temperature gradient formed, warmer near the top, cooler below. This layering created stratification, a structure necessary for later chemical concentration. Yet constant storms kept breaking and reforming the layers, preventing stability from lasting too long. The world hovered between mixing and separation. Meanwhile, rain continued dissolving minerals from volcanic islands that rose briefly above the sea. Every eruption created fresh rock. Every storm ground it down chemically. Rivers carried iron, magnesium, calcium, phosphorus, and trace elements into the oceans in immense quantities. The ocean darkened further, thick with dissolved compounds. If observed closely, its color would not be blue but greenish-black under gray skies, sometimes tinted rusty red near hydrothermal regions where iron oxidized. Waves carried microscopic particles everywhere. The water was not yet friendly to life, but it was becoming chemically interesting. Lightning above added complexity. Electric discharges converted atmospheric nitrogen into reactive forms that dissolved into rainfall. Sulfur gases from volcanoes oxidized into acids, entering the sea and reacting with minerals. Carbon dioxide continuously dissolved, forming carbonates that settled slowly onto the seafloor. The rain was altering the crust through chemistry. Rock interacting with water locked carbon into minerals, gradually reducing atmospheric greenhouse gases. As carbon dioxide decreased, temperatures dropped slightly more. Cooling allowed more vapor to condense permanently into oceans. Another feedback loop strengthened. The sky was losing its water. Pressure decreased noticeably on geological timescales. The crushing atmospheric weight of early Earth slowly relaxed. The boiling point of water lowered with it, but overall cooling compensated, allowing oceans to remain stable. For the first time in planetary history, the atmosphere was trending toward transparency, not clear yet, but thinner than before. Through rare gaps in the clouds, the sun appeared brighter. Its light reflected across the vast ocean surface, scattering into a dim silver glow visible beneath storm layers. Night also changed. Instead of constant darkness broken only by lightning, faint starlight occasionally penetrated thinner cloud patches. The universe was becoming visible from the surface. Yet the rain still persisted, because evaporation and condensation remained the primary way Earth shed internal heat. Hydrothermal vents along the ocean floor released superheated water continuously, forming towering plumes rising kilometers upward. These plumes cooled and mixed with colder seawater, carrying minerals outward in expanding clouds. When storms churned the surface above these vents, deep and shallow waters mixed violently. Heat escaped faster, cooling accelerated again. Over millions of years, ocean depth increased dramatically. Basins filled to capacity. Water spread over low volcanic plains that once stood above sea level. True global oceans formed uninterrupted across most of the planet. Only scattered archipelagos remained above water for long. Tides, driven by the closer moon, swept across these islands daily, submerging and exposing them repeatedly. Rain hammered them constantly. Chemical reactions concentrated along their edges as water evaporated slightly during brief lulls between storms. Shallow coastal pools formed temporary, mineral-rich, repeatedly diluted and concentrated again. The stage was becoming chemically dynamic, and still, even after tens of millions of years, the sky had not emptied completely. Vast cloud systems continued transferring the last great reservoirs of atmospheric water downward. Each century slightly lowered the cloud ceiling. Each millennium slightly brightened the surface. The sky that once held oceans was slowly surrendering them to the planet below, and as it did, the character of the rain began to change once more. By now, the rain had lasted longer than any storm imaginable. Not years, not centuries, but spans of time so large that mountains could have risen and eroded entirely beneath it. Yet, the final phase of this planetary rainfall was the strangest of all, because the rain was no longer trying to cool the planet. It was trying to finish the transfer. Most of Earth's water now resided in the oceans. The atmosphere, once swollen with vapor, had thinned dramatically compared to its earlier state. But it still held vast cloud systems, lingering reservoirs slowly emptying into the sea. The difference was subtle. Storms no longer formed everywhere equally. Instead, the sky began organizing into belts. Near the equator, rising warm air still generated massive storm towers. Rain there remained intense and frequent, but toward mid-latitudes, storms started arriving in cycles rather than permanence. The first long pauses between heavy rains appeared stretches that might last weeks or months before the next great deluge returned. To a future human observer, it would still feel like a world of endless rain. To the planet, it was a revolution, because pauses meant evaporation could briefly compete with precipitation. The hydrological cycle, once one-directional toward the surface, became balanced. Some water now returned skyward without immediately falling back. Clouds thinned and reformed instead of existing as a permanent blanket. The first true weather variability had begun. During clearer intervals, sunlight warmed the ocean surface more efficiently than before. Shallow waters heated faster than the deep ocean beneath them, producing stable layers for longer periods between storms. In these calm windows, dissolved chemicals concentrated locally rather than dispersing instantly. The ocean started developing regions, not just temperature zones, but chemical environments. Near hydrothermal vents, superheated mineral-rich water mixed upward, forming dense plumes. Near coastlines, rainfall carried fresh rock particles downward. In shallow basins, evaporation during calmer periods thickened dissolved compounds further. Each location became slightly different from the others. Earth was diversifying itself chemically. Meanwhile, atmospheric chemistry was also transforming. With less water vapor dominating the air, other gases became relatively more important. Carbon dioxide still ruled the sky, along with nitrogen and volcanic sulfur gases. But reactions with rainwater were slowly removing carbon from the atmosphere and locking it into ocean sediments. The greenhouse blanket weakened. As temperatures dropped gradually, storms lost a small portion of their violence. Winds remained powerful by modern standards, yet no longer stripped entire surfaces of stability. Islands survived longer. Basins persisted for ages instead of centuries. For the first time, coastlines could remain recognizable across generations of geological time. The sky grew lighter still, a muted grey rather than dark orange. The sun appeared daily now, though filtered through thick cloud cover most of the time. Nights revealed the moon clearly, its pull driving enormous tides across the global ocean. Those tides created rhythmic flooding cycles along shallow shores, repeatedly wetting and drying mineral-rich environments. Cycles had entered the world. Day and night cycles of heating and cooling. Tidal cycles of flooding and exposure. Storm cycles of dilution and concentration. These repeating patterns mattered more than the rain itself ever had. They allowed reactions to progress step by step instead of resetting continuously. Molecules formed, broke apart, and formed again in slightly different arrangements. The ocean was no longer just water. It had become a dynamic chemical system. Deep below, hydrothermal vents still erupted steadily. Hot fluids rich in metals and reduced compounds poured into cold seawater, forming steep energy gradients. Above them, Cooler, oxygen-free water circulated downward, carrying surface chemicals into contact with geothermal energy sources. Energy differences are the foundation of complex chemistry, and Earth now possessed them everywhere. In the atmosphere, lightning had not ceased. Though storms were less constant, electrical activity remained frequent. Each strike rearranged atmospheric molecules and injected reactive products into rainfall. These compounds entered the oceans and joined the growing chemical inventory. Millions of years earlier, lightning had struck a hostile surface that erased everything instantly. Now, lightning struck an ocean, capable of storing the result. This storage was crucial, because when molecules persist, they can interact again. Repetition builds complexity. Complexity eventually builds structure. The rain, which once only cooled the planet, had become a delivery network transporting atmospheric chemistry into oceanic reservoirs where it could accumulate instead of vanish. Gradually, the total global rainfall began declining. Not suddenly, no final storm, but through a long reduction in frequency. Some regions experienced extended calm seasons between wet periods. Others remained storm-dominated. The world transitioned from a single climate into many. Earth now resembled a water world rather than a steam world. From orbit, vast oceans reflected sunlight through shifting cloud systems, and dark storm spirals moved like living patterns across the surface. The brightness of the planet increased as cloud thickness decreased overall. Space itself could now see the ocean clearly. The sky had surrendered. Water had completed its descent from atmosphere to surface. The oceans were permanent, deep, and globally connected. Rain still existed, always would, but no longer defined the entire planet's identity. Instead, the oceans defined it, and inside those oceans, enriched for millions of years by endless rainfall, lightning chemistry, volcanic minerals, and tidal cycling, conditions had quietly become suitable for something entirely new. The age of planetary cooling was ending. The age of planetary chemistry was beginning. The longest storm in Earth's history had built more than seas. It had built a laboratory large enough to cover a world. What happened next would not involve fire from the sky, but reactions within the water itself. Even after the skies had surrendered most of their water, Earth did not become a dry world. In fact, for an incredibly long stretch of its history, drying was almost impossible. The reason was simple. The planet now contained too much ocean, and the atmosphere, though thinner than before, still carried enormous moisture compared to modern Earth. Evaporation happened constantly across warm equatorial seas, feeding clouds that traveled across the globe before releasing rain again. Water cycled endlessly, rarely remaining in one place for long. Earth had become hydrologically trapped. Once the oceans formed, they stabilized temperature so effectively that no region could escape the water cycle entirely. There were no deserts, no frozen poles, and no permanent dry land masses. Even volcanic islands that briefly rose above sea level were relentlessly attacked by precipitation. Rainfall softened fresh rock, rivers carved it apart, and waves shattered it into sediments that returned to the ocean. Land could not stay land. Every exposed surface was temporary. If a mountain chain rose, rain eroded it faster than tectonics could build it. If lava hardened into plateaus, Storms fractured it into fragments within geological moments. The planet was smoothing itself under the authority of water. This was a time when continents, as we know them, did not yet dominate the surface. Instead, scattered microcontinents and volcanic arcs appeared and vanished repeatedly. Each one endured an existence measured not in hundreds of millions of years like modern continents, but in mere millions before erosion consumed them. Water ruled geology. And because water ruled geology, it also ruled chemistry. The ocean now covered nearly the entire planet, and its depth had grown immense in places. Beneath its surface, pressure increased dramatically, stabilizing liquid water even at high temperatures near geothermal sources. This allowed hot and cold environments to coexist side by side, one of the most powerful drivers of complex reaction. Near hydrothermal vents, mineral-rich superheated water surged upward from cracks in the crust. Around those vents formed towering mineral chimneys as dissolved metals precipitated upon meeting cold seawater. These structures created natural compartments, tiny cavities where chemicals could concentrate instead of dispersing. The oceans were no longer uniform. They were structured environments filled with gradients, hot to cold, acidic to alkaline, mineral-rich to dilute. Each gradient provided opportunities for molecules to interact differently depending on location. Instead of a single massive chemical soup, Earth now contained countless microscopic laboratories scattered across the seafloor. Meanwhile, the surface above remained restless. Rain continued to fall frequently, though not constantly. Storm belts circled the globe, driven by warm ocean currents and the still powerful greenhouse atmosphere. The sun shone brighter than before, yet thick cloud cover kept temperatures warm and stable worldwide. Polar regions experienced rainfall rather than ice. The planet had not yet discovered winter. Because there was no ice, sea level remained extremely high. Coastlines were shallow and broad, forming vast tidal flats wherever land managed to exist temporarily. Twice each day, driven by the much closer moon tides, surged across these flats, flooding them deeply before retreating again. Pools were isolated, concentrated by evaporation, then diluted by rainfall, then flooded once more. This repetitive cycling mattered enormously. In these pools, minerals and organic molecules could build up to higher concentrations than in open ocean water. When storms arrived, they mixed contents. When tides withdrew, they left behind thin films where reactions occurred faster. Day and night temperature changes further altered conditions. The planet, unable to dry, created wetness in every possible form. Deep sea, shallow sea, tidal pool, mist, rain, steam, and fog. No environment remained static long enough to stagnate. Above the ocean, the atmosphere continued evolving. Carbon dioxide slowly decreased as chemical weathering locked it into ocean sediments. Nitrogen became the dominant gas. Methane and ammonia fluctuated through volcanic activity. Lightning repeatedly energized the mixture, forming reactive compounds that washed into the water below. Energy kept entering the system from multiple sources. Sunlight warming the surface, geothermal heat rising from the crust, electrical energy from storms, tidal energy from the moon. Earth was saturated not just with water, but with energy. And energy in a wet environment rarely stays simple. As time passed, The chemical composition of seawater changed subtly but persistently. Dissolved metals reacted with atmospheric compounds delivered by rain. Some compounds broke apart under ultraviolet radiation during rare clear skies. Others formed chains of increasing complexity in protected environments like hydrothermal cavities or mineral surfaces. The oceans were no longer passive. They were active participants in transformation. Yet despite these internal changes, from the outside the planet still appeared dominated by weather. Clouds moved in sweeping belts around the globe, releasing rainfall across vast regions before reforming elsewhere. Ocean currents transported heat poleward and returned cooled water toward the equator. The cycle never stopped. If an observer could have watched Earth for 1,000 years, they would see storms shifting endlessly, but never disappearing. The world did not dry because its systems prevented stability from favoring dryness. Any region beginning to clear warmed slightly, increased evaporation, formed clouds again, and returned to rainfall. It was a self-sustaining wet equilibrium, and that equilibrium persisted for tens of millions of years. During this time, something subtle but profound was happening beneath the waves. Molecules created in the atmosphere were surviving long enough in the ocean to encounter new conditions repeatedly. Instead of being destroyed instantly by heat, as in the magma era, they circulated, reacted, and recombined. The rain had built the oceans. Now the oceans were beginning to build complexity. Earth had entered a phase where destruction slowed just enough for persistence to exist, and persistence is the first requirement for structure. The planet could not dry, which meant reactions never truly stopped. And where reactions never stop, patterns eventually appear. The longer Earth remained trapped in its wet equilibrium, the more its chemistry began to behave differently from ordinary mixtures. In most environments, chemical reactions occur once, and then end molecules collide, transform, and disperse. But Earth's oceans did not allow dispersal for long. Currents carried products into new environments, tides concentrated them again, storms mixed them back into solution, and geothermal vents re-energized them. Nothing stayed finished. A molecule formed near the surface might sink into warm depths, rise again through convection, wash into a tidal basin, dry slightly under weak sunlight, then dissolve once more during rainfall. Each cycle altered it a little. Not enough to create life yet, but enough to prevent chemical stagnation. Repetition was becoming the dominant force shaping matter. Consider the shallow coastal flats scattered across temporary volcanic islands. When tides withdrew, thin layers of water remained trapped in mineral depressions. Under dim sunlight, some water evaporated. Dissolved compounds became concentrated. When storms returned, they diluted again, but not perfectly. Each concentration-dilution cycle changed reaction probabilities. In chemistry, probability matters more than intention. A reaction unlikely in open ocean might become common in a concentrated pool. Molecules that rarely meet in deep water collided frequently in shrinking puddles. Some broke apart, some bonded weakly. A few formed more stable structures capable of surviving the next dilution. Those survivors traveled elsewhere when tides rose. Across millions of years, the planet performed countless microscopic experiments, simultaneously far beyond anything a laboratory could replicate. Each wave, each storm, each thermal gradient repeated trials without memory, yet built results through persistence. And persistence slowly filters chaos. Meanwhile, deep in the oceans, hydrothermal vents created a completely different environment. There, mineral walls formed porous labyrinths of tiny chambers. Hot, alkaline fluids met cooler, acidic seawater, generating steep chemical gradients across thin mineral boundaries. These gradients stored energy, usable energy, not as heat alone, but as potential differences across microscopic barriers. Inside these cavities, molecules could remain confined. Instead of dispersing into endless ocean volume, they accumulated. Reactions repeated in the same location. Certain arrangements lasted longer because the environment favored them. Iron-sulfur minerals catalyzed bonding between simple carbon compounds. Chains formed, broke, and reformed, sometimes longer than before. The vent systems acted like natural reactors, operating continuously for millions of years. Above, lightning storms provided another ingredient: reactive atmospheric compounds. Nitrogen oxides dissolved into rainwater and reached the sea. Ultraviolet radiation during rare, clear periods energized surface molecules. Volcanic gases injected sulfur compounds everywhere. None of these alone created complexity, but together they increased diversity. Diversity is the raw material of selection. Earth had no biology yet, but it already possessed selection pressure. Structures that survived repeated environmental cycles accumulated, those that did not disappeared. Stability under changing conditions became the first advantage long before survival meant anything biological. The ocean was quietly filtering molecular possibilities. At this stage, the planet still looked hostile beyond imagination. Storms circled endlessly. Waves rose like moving hills across the sea. The air remained unbreathable and carried acidic rains compared to modern standards. Temperatures were warm across the globe, perhaps comparable to tropical waters everywhere, yet stable enough for liquid persistence. Nothing resembling plants or animals existed. But order was beginning to exist. In deeper regions, layered sediments formed as dissolved minerals precipitated slowly from seawater. Thin sheets accumulated on the ocean floor, trapping chemical signatures of reactions happening above. The earliest geological record of chemistry was being written long before fossils could exist. Earth was keeping notes in stone. And still, the inability of the planet to dry played a crucial role. If oceans had retreated, reactions would halt. If the world froze, chemistry would slow to near silence. Instead, warmth and water ensured constant motion. Every molecule remained part of circulation, never isolated permanently, never erased instantly. The system balanced between destruction and preservation. Too violent to stabilize completely, too calm to erase everything. This balance persisted for immense spans of time. During it, certain molecular assemblies began lasting longer than others, simply because they resisted breakdown during environmental change. They were not alive. They did not reproduce, but they endured. Endurance is the first shadow of survival. As storms swept across the world, rainfall continued, carrying new materials into the sea. Iron dissolved from rocks, tinted waters dark in some regions. Silica accumulated elsewhere. Phosphorus, a rare but crucial element, concentrated in certain basins after repeated wet-dry cycles. Each region became chemically distinct. Different environments began producing different results. Some favored simple chains, some favored rings, some destroyed both. The planet was exploring possibilities in parallel. From orbit, nothing about Earth would yet suggest significance. It remained a storm-covered water world under thick clouds, illuminated by frequent lightning. But beneath that restless surface, the chemical network had grown enormously complicated compared to its beginnings. The rain had not merely cooled the planet, it had created endless opportunities for repetition. And repetition slowly reshapes randomness into pattern. Somewhere in these oceans, patterns were getting closer to doing something extraordinary. Not yet life, but approaching behavior that could lead toward it. The world still could not dry. And because it could not dry, its chemistry could not stop evolving. Over immense spans of time, the wet equilibrium of Earth began to produce an unexpected consequence memory. Not memory in the biological sense, memory in chemistry. In ordinary reactions, products disperse and vanish into the environment. But on this planet, where water cycled endlessly and environments repeated themselves, certain molecular arrangements began appearing again and again in similar conditions. The same gradients, the same mineral surfaces, the same temperature ranges, they recreated similar outcomes. The planet was starting to favor familiarity. Along hydrothermal vent walls, iron and sulfur minerals formed structured lattices. These lattices did not merely host reactions, they guided them. When certain carbon compounds attached to their surfaces, they aligned in specific orientations. When new molecules arrived, they attached in predictable ways. For the first time, reactions became partially directed instead of purely random. Elsewhere, in tidal pools, thin films of evaporating water concentrated molecules into layers only micrometers thick. In such tight proximity, chains formed more easily than in the open sea. When storms returned, most chains broke apart, but a few configurations resisted disruption. They dissolved, spread, and sometimes entered another pool, repeating the same cycle. The environment repeated conditions, and the molecules repeated responses. Repetition created preference. Preference created persistence. The oceans now contained molecules that lasted longer simply because their structure fit the planet's rhythms. They tolerated heating and cooling. They survived dilution and concentration. They endured weak ultraviolet radiation during brief, clear skies. Still not alive, but no longer entirely accidental. At the same time, Earth itself continued to evolve physically. The crust thickened enough for larger proto-continents to survive longer above the sea. Rainfall still dominated climate, yet vast, shallow seas formed around these land masses. Rivers transported minerals continuously, creating layered sediments at their mouths. These river mouths became chemical crossroads. Fresh water from rain diluted seawater locally, altering pH levels. Sediments trapped organic compounds washed from the atmosphere. Sunlight penetrated shallow depths during calmer periods. The combination created unique chemical zones, unlike deep ocean vents or open seas. Multiple pathways toward complexity now existed simultaneously. In deep vents, heat-driven reactions in mineral chambers. In tidal flats, concentration-driven reactions under cycles. In shallow seas, sunlight-driven reactions near sediments. The planet was experimenting with different strategies at once. Meanwhile, Atmospheric conditions slowly improved, though still harsh. With more carbon locked into rock and water, the sky cleared slightly further. Clouds remained dominant, but now blue hints occasionally appeared between storm systems. Sunlight reached the ocean surface more often, energizing surface chemistry in ways previously impossible. Light added another energy source. Unlike geothermal heat or lightning, sunlight arrived gently but constantly across vast areas. Certain molecules absorbed its energy and changed shape. Some broke apart, others formed stronger bonds. Over time, molecules capable of handling light without destruction accumulated where illumination occurred frequently. Energy tolerance became another form of endurance. Through all this, the hydrological cycle continued, uninterrupted. Rain fell, rivers flowed, tides churned, vents heated, and evaporation lifted water skyward again. The world never paused long enough for chemical progress to reset completely. Earth's inability to dry had created continuity. Continuity allowed accumulation. Accumulation allowed complexity. And complexity was approaching a threshold. Some molecular networks now influenced nearby reactions. When certain compounds formed, they made it easier for similar compounds to form nearby. Not true replication, but facilitation. Patterns began assisting their own reappearance simply by existing in the right environment. The first hint of self-organization had emerged. The ocean had transitioned from a passive chemical mixture into an interacting system. Local regions began developing chemical identities shaped by their condition. The planet was no longer just running experiments. Some experiments were starting to reinforce themselves. Given enough time, reinforcement leads to propagation. And propagation, under the right circumstances, becomes life. The storms still circled overhead, though gentler than in ages past. Rain continued feeding oceans that now held the cumulative results of millions of years of chemical processing. The longest rain in Earth's history had not only filled the seas, it had sustained the reactions needed for increasing order. The planet that could not dry had unknowingly built the continuity necessary for the next transformation. Soon, somewhere in those restless waters, chemistry would cross a boundary it had never crossed before. Not a sudden miracle, not a single moment, but the gradual emergence of something capable of persisting not just through environment, but through time. The rain had prepared the world. The oceans had prepared the molecules. And the molecules were nearing the point where they would begin preparing themselves. Long before life could begin, Earth first had to achieve something deceptively simple. Stability. Not calm weather storms still ruled the sky. Not comfort, the air remained toxic and heavy, but stability in the relationship between rock and water. For hundreds of millions of years, oceans had been forming, deepening, and spreading. Yet they were still temporary in a geological sense. Entire regions boiled away after massive impacts. Volcanic resurfacing replaced seafloor with molten rock. Basins shifted as the crust rearranged itself. Water existed, but it had not yet truly settled. Then the planet crossed another threshold. The bombardment from space declined. In earlier ages, leftover debris from the formation of the solar system had struck Earth constantly. Each impact reheated the crust locally and sometimes globally. But as time passed, the inner solar system cleared. Fewer objects remained to collide with the planet. millions of years began passing without world-resetting impact. For the first time, Earth was allowed to keep its oceans. This did not mean tranquility. Volcanoes still erupted across the surface and seafloor, releasing heat continuously. Yet now their energy was localized. The ocean could absorb it without disappearing. Instead of returning the planet to steam, eruptions merely stirred the water above them. The balance had shifted permanently. The oceans were no longer temporary features, they were structural features of the planet. Across vast lowlands, water stretched uninterrupted for thousands of kilometers. Only scattered volcanic chains broke the horizon. From orbit, Earth now reflected sunlight in broad metallic glimmers beneath moving cloud layers. The moon's tides rolled across a true global ocean whose depth in places exceeded several kilometers. But these oceans did not resemble modern seas. They were darker, denser, and chemically rich. Dissolved iron colored many regions greenish or rusty brown. Suspended particles filled the water column. The sky's faint light penetrated only shallow depths, leaving the deep ocean in permanent darkness, broken only by geothermal glow near vents. And everywhere the water moved. Powerful currents formed as equatorial warmth met cooler polar regions. Warm surface water drifted poleward, while cooler depths returned toward the equator. Vertical convection lifted minerals upward and sank surface compounds downward. The ocean circulated constantly, distributing heat and chemistry across the planet. Earth had become a single connected system. Meanwhile, continents began attempting permanence. The thickening crust allowed larger land masses to survive above sea level for longer intervals. These proto-continents were low, flat, and unstable compared to modern ones, but they endured millions of years instead of thousands. Rainfall carved valleys across them, transporting sediments into surrounding seas. Shorelines migrated slowly rather than vanishing instantly. This created something new. Long-lasting coastal zones, where land met ocean, waves ground rock into fine particles. Rivers delivered minerals continuously. Tides mixed fresh and salt water repeatedly. Such zones became among the most chemically diverse environments on the planet. Here, the oceans interacted directly with the crust. Chemical weathering intensified. Carbon dioxide dissolved in rainwater reacted with silicate rocks, locking carbon into minerals that washed into the sea. Over immense timescales, this process reduced atmospheric greenhouse gases further, allowing gradual cooling. The sky lightened again. Clouds still dominated, but now sunlight regularly reached the surface. The ocean's surface shimmered under dim but persistent illumination. Day and night cycles became clearer distinctions instead of perpetual gloom. And as sunlight increased, surface waters warmed slightly more than depths. This allowed stratification to last longer between storms. A thin upper layer of warmer water floated above cooler deep ocean, creating stable conditions where reactions could persist without immediate mixing. Storms still disrupted the layers, but they reformed afterward. The oceans had begun developing internal structure. Deep below, hydrothermal vents continued pumping minerals into seawater, but now their plumes spread through layered water rather than mixing instantly everywhere. Chemical gradients sharpened, regions became more distinct in composition, complex chemistry prefers difference, and the oceans were gaining it. Above, the hydrological cycle continued its long transformation. Rain still fell frequently, but the planet no longer drowned beneath continuous downpour. Instead, cycles appeared: storm seasons, calmer periods, and shifting wind patterns. The longest storm in Earth's history was ending not with the final rain, but with variability. The sky had learned moderation. The amount of water moving between ocean and atmosphere stabilized. Evaporation roughly balanced precipitation globally. Local imbalances drove weather rather than planetary cooling. Earth's temperature settled into a range suitable for liquid persistence everywhere on the surface. Water had fully claimed the planet. This stability did something profound. It allowed chemical progress to accumulate across millions of years without reset. No more global boiling oceans, no more complete evaporation eras. Reactions could now build upon previous reactions continuously. The oceans were no longer temporary experiments. They were permanent laboratories, and inside them, the products of endless rainfall, mineral weathering, geothermal energy, and sunlight had reached concentrations never before sustained on the planet. The stage was finally steady enough. Now chemistry could begin attempting something far more delicate than ocean formation organization, because once the oceans truly existed, they began trying to create inhabitants. With the oceans now permanent, time itself became the most powerful ingredient Earth possessed. Before stability, chemistry had to restart repeatedly, boiled away, shattered by impacts, or mixed too violently to persist. Now reactions could continue uninterrupted for spans longer than mountains existed in earlier ages. The difference was not just duration, but continuity. Each cycle of tides, sunlight, and geothermal heat built upon the previous one rather than erasing it. The ocean began to remember, not consciously, but structurally. Certain regions accumulated particular compounds because currents carried similar materials there again and again. River mouths gathered sediments. Shallow basins concentrated dissolved salts during evaporation. Vent fields stored mineral-rich fluids in porous rock networks. Each place developed chemical character. Near hydrothermal vents, hot alkaline fluids rich in hydrogen and metals flowed into cooler, slightly acidic seawater. The contrast created natural electrochemical gradients across mineral barriers, a continuous source of usable energy at microscopic scales. Inside vent pores, molecules repeatedly formed and broke apart, guided by mineral surfaces acting like primitive catalysts. Elsewhere, in sunlit shallow seas, ultraviolet light drove different reactions. Simple carbon compounds absorbed energy and rearranged into more complex shapes. Most decomposed quickly, but some endured long enough to interact with new compounds arriving through rain and rivers. The surface favored light-driven chemistry, the depths favored heat-driven chemistry, and tides connected them. Twice each day, coastal waters mixed deeper materials upward and carried surface molecules downward. Pools isolated during low tide concentrated compounds further. When the tide returned, it dispersed them into broader ocean regions, seeding new reactions elsewhere. Earth was distributing its experiments globally. Meanwhile, the atmosphere had grown calmer compared to its violent youth. Storms still formed, but they no longer covered the entire planet simultaneously. Large cloud systems moved along predictable paths. Periods of partial clearing allowed more sunlight to penetrate the upper ocean, warming it and strengthening temperature layers. This layering created calm microenvironments beneath the surface, thin regions where mixing slowed enough for fragile structures to last longer than before. Fragility could now exist, briefly, without immediate destruction. In these calmer waters, some molecules began forming films at the boundary between water and air. Surface tension concentrated them there naturally. When waves broke, these films shattered and reformed repeatedly, testing which arrangements survived mechanical stress. Survival here meant persistence against motion. At the same time, dissolved metals like iron and magnesium interacted with organic compounds delivered by rain and lightning chemistry. Mineral particles acted as scaffolds where molecules attached, detached, and reattached in different patterns. Certain configurations resisted breakdown slightly better under ultraviolet radiation or temperature shifts. Earth was unintentionally selecting stability. Nothing yet reproduced, nothing metabolized, but endurance increased. In deeper ocean layers, pressure stabilized large molecules that would fragment near the surface. Near the surface, sunlight energized reactions impossible in darkness. The ocean offered multiple testing grounds simultaneously, each eliminating different weaknesses. Gradually, a class of molecules appeared that could influence surrounding reactions not by intent, but by structure. When present, they made similar molecules easier to form nearby. They were not alive, yet they shaped their environment in subtle ways. Self-favoring chemistry had emerged. Meanwhile, geological processes continued altering the environment. Proto-continents grew larger and lasted longer. River systems extended hundreds of kilometers before reaching the sea. Sediments accumulated in thick layers, trapping chemical products and preserving them from immediate destruction. Some compounds that would once vanish now lingered in sheltered environments for ages. The ocean floor itself became a record of progress. Layer upon layer of mineral deposits captured the chemical evolution happening above. Over millions of years, the concentration of complex carbon compounds in certain regions increased measurably. The planet was slowly shifting from purely inorganic chemistry towards something approaching organized networks. All of this occurred under a sky still filled with clouds and rain, but rain now played a different role. Instead of cooling a molten world, it delivered trace elements continuously into stable oceans. Phosphorus from rocks, nitrogen from atmospheric reactions, sulfur from volcanoes. Each storm replenished ingredients without resetting condition. The longest rainfall in history had transformed into a supply chain. Energy flowed from the sun, the moon, and the planet's interior. Materials flowed from sky to sea and back again. Given enough repetition, complex systems begin crossing thresholds unexpectedly. Somewhere in these oceans, reactions were beginning to persist, not only because the environment allowed them, but because their own structures reinforced their continuation. Earth's oceans had become permanent. Now permanence was beginning to appear within the chemistry itself. The next change would not reshape the planet's surface. It would reshape what the planet contained. Once stability lasted long enough, the oceans stopped behaving merely as environments and began behaving as systems. In the earlier stages, Earth dictated chemistry entirely. Heat destroyed structures, Impacts reset reactions, and storms mixed everything into uniformity. But now, after tens of millions of years without planetary-scale interruption, certain chemical arrangements began influencing their surroundings in return. The difference was subtle at first. Some molecular clusters remained intact longer within mineral pores near hydrothermal vents, not because they were protected perfectly, but because their structure matched the local conditions, temperature, pH, and available energy gradients. When new molecules drifted into those pores, they tended to join similar patterns rather than random ones. The environment selected them, and they selected themselves. Elsewhere, in shallow tidal zones, evaporation cycles concentrated thin organic films repeatedly. Each drying phase encouraged bonds to form. Each rehydration phase tested whether those bonds held. Most arrangements failed, but a few resisted disruption and returned intact when water flowed back. Persistence became cumulative. Over immense spans of time, these stable arrangements appeared in multiple places across the planet, not identical, but similar enough that they interacted in predictable ways when currents mixed them. Earth's chemistry was no longer purely chaotic. It was developing tendencies. Tendencies can become processes. Near vent systems, mineral surfaces created compartmentalized microspaces where energy gradients were continuous. Hot fluids provided chemical fuel, and cooler ocean water removed waste products. In these confined spaces, reactions could proceed in sequences, one reaction preparing conditions for the next. Sequence was the crucial innovation. Instead of isolated events, chains of reactions began repeating in order whenever materials cycled through the same environment. They were still fragile and easily disrupted, but the constant motion of water returned ingredients again and again. The ocean was rehearsing. Above, the sky had grown noticeably brighter than in earlier ages. Thick cloud layers remained, yet sunlight now penetrated daily across broad regions. The water surface glimmered dimly rather than glowing only under lightning. Temperature differences sharpened between day and night, enhancing convection currents that transported surface products downward. Energy entered the system rhythmically. Day warmed surface layers, night cooled them. Tides mixed them, vents energized them. Rhythm allowed predictability. Predictability allowed repetition. Repetition allowed progression. Some molecular networks began lasting long enough to affect subsequent cycles. When storms diluted concentrations, remnants remained on mineral surfaces. When evaporation returned, those remnants served as starting points instead of starting from nothing. Over time, certain reaction pathways became statistically favored simply because they had already occurred before. The ocean had developed a primitive chemical inheritance. Not genetics, not yet, but continuity of structure through environment rather than design. Earth had crossed from random chemistry into historical chemistry, where the past influenced the future. The planet's inability to dry had enabled this transition. Continuous water movement ensured molecules traveled, but were never completely erased. Every basin, vent, and shoreline acted like a memory location storing partial results until conditions returned. Gradually, some molecular assemblies began shaping local chemistry actively. Their presence altered pH or bound minerals differently, affecting how new compounds formed nearby. Instead of merely surviving conditions, they were modifying them. Influence had appeared. Once influence exists, feedback follows. And feedback drives complexity faster than chance alone ever could. Throughout the oceans, countless microenvironments hosted these feedback loops simultaneously. Most remained short-lived, collapsing after environmental change. But the longest-lasting ones endured multiple cycles, tides, storms, temperature shifts, and reappeared in similar forms elsewhere as currents spread their components. Patterns were propagating across the planet without being alive. Earth's oceans, born from millions of years of relentless rain, had matured into a dynamic network where matter interacted across time as well as space. The transition from formation to organization was nearly complete. Soon, one class of patterns would cross a boundary that none before had crossed, maintaining itself not just by environment, but by producing copies of its own arrangement using surrounding materials. When that happened, the ocean would no longer merely contain chemistry. It would contain activity. The longest storm in Earth's history had ended in a quiet transformation, not the silence of dry land, but the steady rhythm of water-supporting processes capable of persistence. The oceans had fully appeared. Now something within them was preparing to appear as well. Once the oceans stabilized and chemical memory began accumulating, Earth entered a stage unlike any before it, a world filled not just with reactions, but with ingredients. For hundreds of millions of years, rain had carried dissolved minerals from rock into the sea. Lightning had rearranged atmospheric gases into reactive compounds. Hydrothermal vents had injected metals and energy continuously. Sunlight now added gentle but persistent stimulation to surface waters. All these processes shared a single outcome. The ocean was no longer simple water. It had become a chemical reservoir of extraordinary diversity, a global solution containing carbon compounds, nitrogen compounds, sulfur compounds, phosphates, dissolved metals, and countless intermediate forms created and destroyed through endless cycles. If one could sample a drop from different regions of the planet, no two would be chemically identical. In deep vents, water carried hydrogen-rich molecules formed through rock-water interactions. In shallow tidal flats, evaporation concentrated carbon chains delivered by rainfall. In sunlit regions, ultraviolet radiation reshaped molecules faster than in darkness. Everywhere, currents mixed the results. Earth was cooking continuously. The phrase primordial soup would later describe this stage, but the word soup understates the scale. This was not a pot, it was a planetary ocean stirred by storms, heated from below, energized from above, and replenished by the sky itself. And importantly, it never stopped mixing. In earlier eras, violent turbulence prevented accumulation. Now turbulence had structure. Ocean currents circulated materials predictably. Warm surface flows traveled thousands of kilometers before sinking. Deep currents rose elsewhere, carrying minerals upward again. A molecule formed in one region could eventually reach every ocean basin. This global circulation mattered, because reactions occurring in isolation rarely grow complex, they stagnate or collapse. But when products from one environment reach another with different conditions, new possibilities emerge. Earth's oceans were connecting experiments together. Near hydrothermal vents, carbon dioxide reacted with hydrogen to form simple organic molecules, methane, formate, and small carbon chains. These drifted upward into cooler waters where different reactions occurred. Some combined into larger structures. Most broke apart again. But a fraction survived long enough to travel further. In shallow seas, these compounds encountered sunlight and minerals washed from continents. Ultraviolet energy rearranged bonds. Metal ions stabilized certain configurations. Rainfall added fresh reactants constantly. The ocean was layering chemistry upon chemistry. The sky still played its role. Though no longer a crushing steam blanket, the atmosphere remained active. Lightning storms frequently crossed warm regions, converting nitrogen gas into reactive nitrogen oxides. Rain dissolved these compounds and carried them downward. Nitrogen, essential for later biological molecules, steadily accumulated in seawater. Every storm fed complexity. Meanwhile, phosphorus entered the system through weathered rock. Though scarce, it concentrated in certain basins through repeated wet-dry cycles along coastlines. When combined with carbon chains and nitrogen compounds, new molecular possibilities appeared, ones capable of storing energy in chemical bonds more effectively than simpler structures. Energy storage was the next step beyond reaction. Simple molecules react and disperse. Complex molecules can hold energy temporarily. In warm, shallow waters, waves continuously formed thin films where compounds gathered. When the film compressed during evaporation, bonds formed more easily. When waves returned, fragments dispersed, carrying pieces of those structures elsewhere. Most fragments meant nothing, but repetition favors rare events. Over immense spans of time, the ocean accumulated molecules with greater structural stability rings, branching chains, and paired configurations able to withstand heat fluctuations better than their simpler ancestors. They still did not reproduce. Yet they lasted long enough to influence subsequent chemistry. The soup was thickening. At the seafloor, vent systems continued operating as natural reactors. Mineral surfaces catalyzed reactions impossible in open water. Tiny compartments trapped molecules long enough for sequences to proceed stepwise instead of randomly. Chemical pathways began repeating more reliably. The ocean now contained both diversity and direction. This combination was powerful. Diversity provided possibilities. Direction preserved successful arrangements. The result was gradual emergence of networks, groups of reactions, feeding into one another rather than isolated events. A molecule formed here might become the input for another reaction elsewhere, whose product later returned to feed the first. Loops appeared. Loops create continuity. Though still fragile, these loops marked a shift from chemistry that merely happened to chemistry that sustained itself temporarily. Earth's oceans had moved beyond random synthesis toward organized interaction. All of it powered by water, the same water that once fell endlessly from the sky to cool a molten planet. The longest rain in history had not only created oceans, it had filled them with possibility. As the ocean's chemical diversity increased, another transformation quietly unfolded. Molecules stopped acting as isolated participants and began behaving as communities. At first, reactions formed simple products that drifted apart almost immediately. But over long time scales, certain combinations of molecules proved compatible. When they encountered each other again, they reacted along familiar pathways instead of unpredictable ones. These pathways repeated more often than chance alone would suggest. Chemistry was developing habits. Near hydrothermal vents, mineral pores provided continuous energy gradients. Hydrogen-rich fluids rising from deep rock met carbon dioxide dissolved in seawater, producing simple organic molecules. On their own, they were unstable in open ocean water. Yet inside vent cavities, products accumulated long enough to react again before dispersing. Instead of one reaction producing one molecule, sequences appeared, one product becoming the reactant for the next. Outside the vents, ocean currents carried these products into cooler water layers where different reactions became favorable. Some molecules combined into ring-like structures that resisted breakdown. Others formed chains capable of folding into stable shapes under specific temperatures. The ocean now contained shape-dependent chemistry. Shape matters because structure determines behavior. Certain folded molecules shielded sensitive bonds from water, allowing them to last longer. Others bound to metal ions, stabilizing themselves further. The most durable persisted through currents and storms, spreading across wider regions. Persistence allowed accumulation. In shallow coastal flats, daily cycles intensified the process. When tides withdrew, pools evaporated slightly under dim sunlight. Concentration increased dramatically compared to open ocean conditions. Molecules that rarely met in dilute seawater collided frequently here. Some linked temporarily. Most separated again when water returned, but occasionally bonds formed that resisted dilution. Those structures re-entered the ocean intact and circulated globally. Over time, oceans became seeded with recurring molecular patterns formed originally in localized environments. Earth was sharing chemical innovations across its surface. Meanwhile, atmospheric reactions continued, supplying new materials. Lightning converted nitrogen gas into reactive forms, dissolving in rainwater. Volcanic gases contributed sulfur compounds. Weathering added phosphorus. Each input expanded the range of possible interactions. The chemical soup never ran out of ingredients. With growing diversity, interaction networks thickened. Instead of a few reaction pathways, thousands coexisted simultaneously. Some interfered with each other. Some reinforced each other. A few created feedback loops, products that enhanced the likelihood of their own formation indirectly by stabilizing related molecules. Feedback changed the nature of the ocean. In purely random chemistry, equilibrium dominates reactions slow as balance is reached. But feedback prevents equilibrium. Systems keep moving, driven by continual inputs of energy and material. Earth's ocean became a non-equilibrium environment where certain molecular assemblies lasted longer because the system kept recreating them. Time now favored complexity rather than simplicity. At microscopic scales, films forming on mineral surfaces acted as temporary platforms. Molecules arranged themselves side by side according to electrical attraction and shape compatibility. When disturbed by waves, fragments carried portions of those arrangements into new locations where they could reform. Fragments retained partial structure. Partial structure meant reactions started closer to completion than from raw materials. Over countless repetitions, this reduced randomness. The ocean slowly shifted from exploring possibilities to refining them. Refinement is the precursor to replication. Not true copying yet, but pathways existed where similar structures repeatedly appeared because conditions favored them strongly. Given enough cycles, probability concentrated towards specific arrangements, the planet was narrowing its options. Deep waters, surface films, tidal pools, and vent cavities all contributed pieces of this process, none alone sufficient. Together they formed a network spanning the globe. Materials traveled between environments, each altering them differently but rarely destroying them completely. Earth had created a layered laboratory, operating in parallel. And through all of this, the rain still fell. Not as the catastrophic deluge of early ages, but as persistent weather delivering trace elements and maintaining circulation. Without it, rivers would stop, mineral supply would halt, and chemical diversity would shrink. The ancient rainfall continued to sustain the soup long after oceans had formed. Water was still the engine. Gradually, some molecular groups began influencing how nearby molecules arranged themselves simply by their presence guiding rather than forcing reactions. This was not life, but it was no longer passive chemistry either. The ocean was beginning to organize itself from within. A final threshold remained, one where patterns could not only persist, but reproduce their structure using surrounding materials. The chemical soup was approaching the moment when it would stop being only a mixture and start becoming a process. By now, Earth's oceans have spent immense spans of time accumulating molecules, testing them, breaking them apart, and assembling them again. Most combinations still dissolve back into randomness, but the conditions were no longer neutral. The environment had begun favoring certain arrangements repeatedly, and repetition, given enough time, becomes inevitability. Across tidal flats, hydrothermal vents, and mineral surfaces, some molecular networks reached a new level of stability. Instead of merely surviving environmental change, they started guiding how new molecules assembled nearby. When fragments broke off, they did not disperse uselessly. They encouraged similar patterns to reform in surrounding material. The difference was subtle but profound. Before, structure appeared because conditions allowed it. Now, structure appeared because existing structure influenced it. Chemistry had begun leaning toward continuity. In shallow waters where evaporation cycles concentrated compounds, thin films formed on the surface, delicate layers, only molecules thick. Within these films, certain molecules aligned side by side due to electrical charges and shape compatibility. When waves disturbed the film, pieces broke away, each carrying a portion of the arrangement. When those pieces landed elsewhere under similar conditions, they reorganized into the same pattern more easily than random mixtures. Patterns were spreading. At hydrothermal vents, mineral compartments played a different role. Here, energy gradients across microscopic walls provided constant chemical fuel. Some reaction networks consumed energy from these gradients while maintaining their structure. When fragments escaped the compartment, the pattern inside quickly reformed because surrounding molecules still followed the same pathway. The system restored itself. This restoration marked a turning point. Persistence was no longer passive endurance, it was active reappearance after disruption. Still not alive, but approaching behavior that resembled it, The ocean had become a planet-wide network of semi-stable chemical cycles. Materials circulated globally, but certain patterns kept re-emerging because the environment and the patterns reinforced one another. Stability and reproduction were converging. Then came the importance of boundaries. Some molecules, naturally arranged into spherical clusters when placed in water, their outer surfaces interacting differently with the liquid than their inner parts. These clusters trapped other molecules inside temporarily. They formed, broke apart, and formed again constantly in the ocean. Most clusters meant nothing, but occasionally clusters captured parts of a repeating reaction network. When they split, both halves carried similar internal compositions. Not true reproduction, yet a primitive division-preserving structure more than chance would allow. Containment had entered chemistry. Boundaries prevented dilution. Instead of dispersing instantly, molecules stayed near one another long enough for reaction cycles to continue. Each time the cluster reformed, the internal pattern restarted faster than before because pieces already existed. Repetition accelerated. With enough cycles, some assemblies began maintaining their internal composition longer than surrounding mixtures. Environmental change still destroyed them eventually, but they lasted significantly longer than random arrangements. They represented islands of order in a turbulent chemical sea. The soup was no longer uniform. It contained pockets where chemistry behaved differently, not random, not fully alive, but organized enough to persist through repeated disturbances. These pockets spread gradually as fragments drifted across oceans and encountered compatible conditions elsewhere. Earth had produced self-sustaining chemical patterns. They did not yet evolve. They did not yet compete. But they endured and reappeared. Given more time, endurance would turn into continuation, and continuation into inheritance. The step between chemistry and biology was narrowing to almost nothing. All of it traced back to the ancient rain. The rainfall had cooled the planet, formed oceans, carried minerals, powered cycles, and maintained continuity long enough for complexity to accumulate. Without millions of years of a world that could never truly dry, such fragile organization could never survive long enough to matter. Now, in countless microscopic environments across the global ocean, chemistry was on the verge of crossing a boundary it had never crossed before. The next stage would not just repeat pattern, it would preserve them across generations. And at that moment, the ocean would no longer be merely a chemical soup, it would contain the first true inhabitants of Earth. For hundreds of millions of years, Earth had been preparing a transition so gradual that no single moment marked its beginning. There was no flash of light, no sudden creation. Instead, life emerged as a continuation of chemistry, a pattern that finally refused to disappear. Across the oceans, countless microscopic reaction systems had formed and collapsed endlessly. Most lasted briefly before dispersing into the surrounding water. But a few had reached a new condition. They not only persisted, they restored themselves using materials nearby. This restoration was different from ordinary chemical stability. A stable crystal remains unchanged because nothing disturbs it. These new systems survived because they rebuilt themselves after disturbance. Within mineral pores near hydrothermal vents, chemical networks began cycling continuously. Energy flowed from hot, mineral-rich fluids into cooler seawater, driving reactions forward repeatedly. When portions of the network broke apart, the remaining structure guided surrounding molecules back into the same arrangement. Structure was now maintained through activity. Meanwhile, in shallow waters, spherical molecular clusters, fragile boundaries, formed naturally in water, trapped reaction networks inside. These boundaries were imperfect. They leaked and reformed constantly. Yet occasionally they divided, and each half carried a similar internal composition. This was not perfect copying, but it was close enough. For the first time on Earth, a chemical system produced multiple versions of itself more often than random chance alone could explain. Some versions were slightly different, assembled from similar but not identical components, and those differences affected how long they endured. Persistence began varying between copies. Where variation exists, selection inevitably follows. In the vast ocean, most early systems vanished quickly, but those that maintained internal reactions longer spread further simply because they existed longer to be carried by currents. When they broke apart, fragments seeded nearby environments, restarting similar cycles. The ocean had entered a stage of chemical propagation, still microscopic, still fragile, but now directional. These earliest entities had no cells as modern organisms do, no DNA, no metabolism recognizable today. Yet they shared the essential feature of life, a boundary separating inside from outside while maintaining internal processes that rebuilt themselves. They were chemical systems capable of persistence through reproduction-like behavior, deep in vent regions. Some relied on mineral energy gradients, harnessing chemical differences between fluids to sustain reactions continuously. In surface waters, others relied on sunlight-driven chemistry. Different strategies appeared simultaneously because the planet offered many environments. Life did not start once. It began many times, but only some pathways endured. Those that endured gradually improved at maintaining internal order. Boundaries became slightly more reliable. Reaction cycles became slightly more efficient. Systems that consumed available energy better lasted longer before breaking apart. Time favored improvement without intention. Generations were not counted in years, but in reaction cycles, formation, division, dispersal, reformation. Over immense durations, complexity increased step by step. Certain molecules began storing instructions for rebuilding the system more reliably than random assembly. Information had entered matter. The earliest living things were closer to chemical vortices than organisms self-maintaining patterns in flowing water. Yet they represented a fundamental shift. The planet now contained entities whose continuation depended on their own structure rather than solely on environmental repetition. Earth had produced its first inhabitants. Above them, rain still fell across the ocean's surface, though no longer endlessly catastrophic. It delivered nutrients from land, stirred surface layers, and ensured circulation, carried these primitive life forms across the globe. The ancient storm had done more than shape the world. It had sustained the conditions necessary for life's emergence long enough for persistence to take hold. From this point onward, evolution, the gradual improvement of self-maintaining systems, would begin its slow, relentless course. And it all started not with creatures, but with chemistry that learned to continue. Once persistence began, change became unavoidable. The earliest living systems were fragile, easily disrupted by temperature shifts, dilution, or chemical interference. But they possessed one crucial advantage over ordinary molecules. They could rebuild. Even imperfectly, even slowly, rebuilding meant survival beyond a single reaction cycle, and survival created history. Each time a system divided and produced similar versions of itself, tiny differences appeared. Some variants lasted slightly longer inside turbulent currents. Others resisted heat better near vents. A few held their boundaries more tightly in shallow pools exposed to sunlight. None were trying to adapt, yet the ocean selected them anyway. In the deep sea, energy came from chemical gradients rather than sunlight. Mineral-rich fluids rising from the crust carried hydrogen and metals that fueled internal reactions. Systems able to use this energy continuously endured in darkness, independent of surface conditions. These were among the most stable early forms anchored near vent networks, where resources flowed endlessly. At the surface, a different challenge existed. Sunlight both helped and harmed. Ultraviolet radiation broke apart many fragile structures, yet it also powered new reactions. Some primitive organisms accidentally incorporated molecules that absorbed harmful radiation and released excess energy harmlessly. Those versions survived longer under illumination and spread across brighter waters. Protection became advantage. Elsewhere, in shallow tidal zones, repeated flooding and drying favored systems capable of enduring concentration changes. When water evaporated, many structures collapsed, but certain variations reorganized quickly once water returned. Over time, they dominated these environments simply because they restarted faster after disruption. Speed became advantage. Gradually, a primitive ecology formed, not visible, not dramatic, but real. Different environments favored different survival strategies. Deep vent dwellers thrived on chemical energy. Surface dwellers tolerated light. Coastal dwellers endured change. Life diversified before it became noticeable. Meanwhile, the chemistry inside these early entities grew more organized. Some molecules acted as templates, guiding the formation of similar molecules nearby more accurately than random assembly. This improved reliability of rebuilding after division. Reproduction grew more faithful, still imperfect, still prone to change, but increasingly consistent. Variations now accumulated rather than vanishing instantly. A structure that improved endurance passed its advantage forward because copies resembled the original more closely. Information had begun persisting across generations. This marked the true beginning of evolution, not merely survival of stable chemistry, but gradual refinement of systems capable of storing instructions for rebuilding themselves. No consciousness, no intention, only statistical success across immense time. Above them, the planet continued its cycles. Storms circulated nutrients. Rivers carried minerals into the sea. Tides mixed environments repeatedly. The world that once prevented stability now supported continuous adaptation. Rain still played its ancient role. It transported elements from land into ocean, replenishing resources consumed by growing populations of microscopic life. Without that supply, early ecosystems would stagnate, The longest rainfall in history remained part of life's support system even after its violent phase ended. Slowly, some organisms improved energy usage. Instead of relying solely on external chemical gradients, they captured energy stored in certain molecules and used it to maintain their internal structure longer between divisions. Efficiency became another advantage. Longer survival meant more opportunities to divide. Over countless generations, far beyond human comprehension, complexity increased. Boundaries strengthened. Internal reactions became coordinated rather than random networks. Life remained microscopic, yet it was no longer merely persistent chemistry. It was organized matter capable of change across time. The oceans, once lifeless reservoirs of reactions, now contained self-sustaining populations, drifting with currents, colonizing new environments, and gradually reshaping the chemistry of the water itself. The planet had crossed the boundary completely. What began as rain cooling molten rock had led, step by step, to systems capable of adapting to the world and eventually altering it in return. Life had taken hold. As generations passed, not counted in years but in countless cycles of division, life slowly shifted from fragile survival to environmental influence. At first, the earliest organisms were passengers of the ocean. Currents carried them wherever water moved. They consumed available energy and materials, but changed little around them. Yet as their numbers increased, their collective chemistry began altering the water itself. Small changes accumulated. Some primitive life forms used dissolved compounds in seawater as energy sources, converting them into new chemical products, individually insignificant, but globally measurable across millions of years. Regions populated heavily by these organisms slowly developed different compositions from lifeless regions. The ocean was being modified from within. Near hydrothermal vents, microbial communities clustered around energy-rich flows. Instead of single drifting systems, populations formed dense concentrations sustained by constant chemical supply. Their metabolic reactions altered local mineral deposition, building layered structures along vent walls. Life was leaving physical traces. In shallow waters, organisms tolerant of sunlight spread widely across illuminated regions. They interacted with dissolved metals and atmospheric compounds delivered by rain. Some reactions released gases as byproducts, which escaped into the atmosphere. Though subtle at first, these emissions gradually influenced atmospheric chemistry. The sky was beginning to feel life's presence. None of these organisms were complex. No eyes, no movement beyond drifting, no awareness. Yet they possessed the defining quality of biology: collective persistence through reproduction and variation. Populations expanded wherever conditions allowed and vanished where they did not. Earth now hosted ecosystems, microscopic but real. Over time, competition emerged naturally. Two systems relying on similar resources could not both dominate indefinitely. Variants using energy more efficiently multiplied faster and replaced less efficient ones. The planet's chemistry favored optimization. Evolution accelerated. More reliable information storage developed within these organisms. Molecular sequences became better templates for reproduction, reducing random errors while still allowing occasional variation. This balance allowed gradual improvement rather than chaotic change. Continuity strengthened. Meanwhile, The environment continued supporting them. Oceans circulated nutrients globally, tides carried populations to new habitats, rain replenished dissolved minerals from land. The same hydrological cycles that once cooled the molten Earth now sustained living chemistry across the entire planet. Water remained life's medium and transport system. With time, some organisms formed cooperative clusters, not multicellular life yet, but communities where nearby individuals benefited from each other's chemical byproducts. Waste from one became fuel for another. Networks formed in which no single organism survived alone as effectively as the group together. Interaction became advantage. The ocean floor accumulated thin layered deposits created partly by these microbial communities. Sediments trapped their remains and preserved chemical signatures of their activity. For the first time, the planet recorded biological influence in stone. Earth had changed permanently. The transition from non-living chemistry to living processes was complete. No dramatic boundary separated them, only a gradual strengthening of persistence, reproduction, and adaptation across unimaginable time. Above, storms still crossed the sky, though gentler than in the planet's youth. Rain continued feeding oceans that now contained not only water and minerals, but countless microscopic organisms drifting through currents. The longest storm in Earth's history had ended in an outcome impossible during the Age of Fire, a living ocean. From this point forward, the planet would never again be purely geological. Every future change, atmosphere, surface, climate, would be shaped not only by physics and chemistry, but by biology as well. The first inhabitants were tiny, silent, and invisible. Yet, they had already begun transforming the world that created them. For most of Earth's early existence, rain had been the planet's dominant force, first as a cooling catastrophe, then as a sustaining cycle. But as life spread across the oceans and geological processes continued reshaping the atmosphere, something extraordinary began to happen. The rain slowly lost control, not suddenly, not dramatically, but inevitably. The reason lay in chemistry, not just volcanic chemistry or ocean chemistry anymore, but biological chemistry. The microscopic inhabitants of the sea were interacting with the atmosphere in ways no storm ever had. Many early organisms relied on chemical reactions involving dissolved gases. Some consumed carbon dioxide and released different gases as byproducts. Others interacted with sulfur or nitrogen compounds. Individually insignificant, collectively planetary. Over millions of years, these reactions altered atmospheric balance. Carbon dioxide, once overwhelmingly dominant, gradually declined further as it became locked into ocean sediments and mineral formations influenced by biological activity. The greenhouse blanket thinned again, and global temperatures slowly decreased, not into freezing, but into moderation. Cooling changed the hydrological cycle. With less heat trapped in the atmosphere, evaporation slowed slightly. Storms formed less violently. Rainfall patterns shifted from near constant global precipitation into regional weather systems. Some parts of the planet experienced extended, clear intervals for the first time in its history. The sky began showing blue. Cloud layers still existed, but they no longer sealed the heavens completely. Sunlight reached the surface daily across wide regions, warming the oceans directly rather than through thick vapor. Nights revealed stars more frequently. The atmosphere had become a sky instead of a ceiling. Weather replaced perpetual storm. Meanwhile, continents had grown more stable. Larger land masses now remained above sea level for tens of millions of years. Rainfall still carved rivers and valleys, but erosion no longer erased entire landscapes instantly. Soil-like sediments accumulated, and shallow coastal seas expanded around them. For the first time, Earth possessed enduring geography. As temperatures moderated further, water vapor in the atmosphere declined relative to liquid oceans. Without overwhelming vapor pressure, the planet could experience clear conditions lasting months or years in certain regions. Storm belts still existed near warm equatorial waters, yet polar regions grew calmer. The age of endless rain was ending. This transformation affected the oceans as well. Reduced storm intensity allowed surface layers to remain stable longer. Sunlight penetrated deeper than ever before. Living organisms in illuminated waters adapted to this new energy source more efficiently, increasing biological activity in surface regions. Life and climate began influencing each other. More biological activity altered atmospheric gases further, which in turn shaped weather patterns. Feedback replaced dominance. The environment no longer forced uniform conditions across the globe. Instead, it responded to processes occurring within the oceans. The planet had gained a climate system. Rain still fell regularly, but now it followed cycles: wet seasons, dry seasons, shifting winds. Rivers flowed continuously, rather than forming and vanishing unpredictably. Lakes appeared inland where geography allowed. For the first time, water gathered not only in oceans, but in varied reservoirs across the surface. Earth was diversifying physically as well as biologically. In some high regions, temperatures cooled enough for occasional frost, rare and temporary, yet a preview of future climates unimaginable during the steam world era. The hydrological cycle had become balanced rather than dominant. The longest storm in history had not stopped. It had transformed into weather. And with that transformation, the planet moved from its formative chapter into a new era, a world where water no longer controlled everything, but supported a complex interaction between atmosphere, ocean, land, and life. The rains had shaped the Earth. Now Earth itself would shape the rains. As the atmosphere continued to change, the balance between ocean, land, and sky became more intricate than at any time before. The planet was no longer dominated by a single overwhelming force. Instead, multiple systems began regulating one another. Rain still fell, but its behavior now depended on temperature differences between regions rather than constant planetary heat release. Warm equatorial waters drove rising air and clouds, while cooler regions allowed air to descend and clear. Circulation replaced chaos. Winds formed stable paths around the globe, guiding storms along repeating routes. Some regions experienced frequent rainfall. Others saw long, dry intervals before the next seasonal storms arrived. The idea of climate zones, once impossible, had emerged naturally from balance. For the first time, parts of Earth could remain dry for extended periods. These dry periods changed geology dramatically. Rock exposed without constant rain hardened and accumulated dust-like particles, carried by wind. Rivers cut deeper valleys rather than spreading shallowly across the surface. Landscapes gained detail, cliffs, basins, plateaus, features that endless precipitation once erased immediately. The surface began remembering its shape. Oceans responded as well. With fewer global storms churning them constantly, surface layers stabilized for longer durations. Sunlight warmed upper waters consistently, strengthening temperature gradients between shallow and deep regions. This layering altered nutrient circulation, creating zones richer in life than others. Life distribution became uneven. Some areas thrived with dense microbial populations, others remained sparse. Ocean currents now transported organisms not just everywhere equally, but preferentially along routes shaped by planetary rotation and continental outlines. Geography had started influencing biology. Meanwhile, atmospheric chemistry shifted further. Biological activity continued, removing carbon dioxide gradually. In some regions, organisms released oxygen as a byproduct of energy capture from sunlight, initially in tiny amounts quickly absorbed by surrounding materials. But over immense time, accumulation began. The sky was quietly changing composition. This change affected weather patterns too. Different gases absorb heat differently. As atmospheric balance evolved, temperature contrasts sharpened between day and night and between latitudes. Storm systems became more structured, resembling recognizable weather cycles rather than endless rainfall. Rain now belonged to the climate instead of defining it. Seasons slowly appeared as the planet's axial tilt interacted with clearer skies. Some regions received more sunlight part of the year, intensifying evaporation and rainfall temporarily before calmer periods returned. The hydrological cycle had matured into a rhythmic system. Water moved predictably. On land, rivers carved permanent channels feeding lakes and shallow inland seas. Sediments accumulated in layers, recording annual variations, the first geological calendars written by weather rather than catastrophe. Earth had gained timekeeping in stone. All the while, life adapted continuously. Organisms specialized for stable, shallow waters differed from those thriving in deep vent environments. Variation expanded. Ecosystems became more complex, though still microscopic to the naked eye. The planet was no longer forming conditions for life. Life was now adapting to conditions of the planet, and because life influenced atmospheric gases, it gradually influenced climate in return. The endless rain of the ancient world could never reappear. The system had evolved beyond that state. Too much water now resided in stable oceans, too much carbon locked into rock, too much biological activity moderating atmospheric balance. The age of planetary storms had ended permanently. From now on, rain would be part of a cycle, not the entire story. Earth had crossed from a world shaped by physics alone into one shaped by interaction, geology, chemistry, and biology entwined. The sky, once an ocean waiting to fall, had become something entirely new, a living atmosphere above a living sea. By the time Earth reached this stage, the ancient storm had become memory written only in stone and water chemistry. Rain still fell across the planet, rivers still flowed, clouds still formed, but the difference was profound. Water was no longer draining from the sky into the oceans. The transfer had finished. What remained was circulation. The atmosphere had stabilized into a lasting structure. Layers formed with distinct roles. The lowest held weather and clouds. Higher regions filtered radiation from space. Instead of a uniform vapor blanket pressing downward, the sky became a dynamic system, regulating temperature and protecting the surface. For the first time, the planet possessed long-term climatic equilibrium. Oceans retained their vast heat capacity, preventing extreme temperature swings. Land masses altered wind paths. Life influenced gas composition. Each component moderated the others. A runaway return to a steam world had become nearly impossible under normal conditions. The ancient rainfall could never restart. Evidence of that age, however, remained everywhere. Sedimentary layers formed from relentless early precipitation lay buried beneath younger rock. Mineral ratios in ancient formations recorded how oceans gradually diluted atmospheric vapor. Even the chemistry of seawater still reflected processes begun during those first storms. The planet carried its history internally. Meanwhile, surface conditions grew increasingly varied. Some regions experienced frequent storms, others extended calm. High latitudes cooled enough for seasonal ice to appear, occasionally something utterly impossible during the endless rain era. Water now existed in three stable forms: vapor, liquid, and solid. This expanded climate complexity dramatically. Ice reflected sunlight, cooling certain regions further. Temperature contrasts strengthened atmospheric circulation. Winds intensified in structured patterns rather than chaotic turbulence. Weather became a global engine, redistributing energy continuously. Earth had learned balance. Life continued adapting alongside it. Microbial populations expanded into nearly every available environment. Deep ocean crust, surface waters, coastal sediments, and eventually damp land margins exposed during low tides. Each niche supported slightly different chemical lifestyles. The biosphere was expanding outward. Rain, once destructive, now supported ecosystems by delivering nutrients across land and sea. Instead of erasing structure, it sustained cycles of growth and erosion that maintained environmental diversity. The same process that once dominated the planet now served it. And with clearer skies, sunlight increasingly drove biological innovation. Organisms capable of capturing light energy spread widely in surface waters, altering atmospheric composition further. Though subtle at first, this change would eventually transform the planet's chemistry entirely in ages to come. The ancient storm had ended, but its consequences had only begun unfolding. Earth was no longer merely a world where rain shaped rock. It had become a world where life, water, air, and land continuously reshaped one another. The era of formation was over. The era of interaction had begun, a planet no longer defined by survival against chaos, but by balance within complexity. And everything that would one day exist, forests, animals, and eventually humans, depended on that forgotten age, when water fell for millions of years and built the conditions for stability. The rains did not simply stop. They became part of a living world. By the end of the ancient storm era, Earth no longer resembled the violent world that had first received the falling sky. What remained was not silence. Rain still existed, oceans still moved, winds still crossed the planet, but permanence had replaced struggle. Water was no longer trying to conquer the surface. It had already done so. and everything that followed would depend on that victory. The millions of years of rainfall had done far more than cool a molten planet. It had reorganized the entire structure of Earth. The crust hardened under constant thermal extraction. The atmosphere lost its crushing density. Oceans deepened until they dominated the surface. Chemical cycles emerged that would never again reset to zero. The planet had gained memory. Every later transformation, continents rising, oxygen appearing, complex life evolving, required a stable foundation. Without permanent oceans, the chemistry necessary for life would disperse too quickly. Without moderated temperature, fragile molecular systems could never persist. Without atmospheric balance, radiation and heat would sterilize the surface repeatedly. The rain had built stability itself. Even long after storms became ordinary weather, the hydrological cycle continued performing the same ancient function, transporting materials across the planet. Rivers carried minerals from rock to sea. Evaporation purified water before returning it as precipitation. Oceans stored heat and redistributed it through currents. The system, first formed during chaos, now maintained order. Consider what Earth might have been without that era. A planet retaining its thick vapor atmosphere would remain too hot for permanent oceans. A planet losing water to space without condensation would dry into barren rock. A planet cooling too quickly without atmospheric cycling might freeze entirely. Instead, Earth reached balance because water spent millions of years moving heat from surface to space efficiently. The ancient rainfall acted as planetary temperature control. As continents slowly expanded over geological time, they interacted with this cycle. Mountain ranges guided winds, valleys directed rivers, lakes formed inland. The hydrological system diversified yet remained unified. All fresh water ultimately returned to the oceans that formed in the Storm Age. The memory of the rain existed in every river. Meanwhile, life, once microscopic, evolved in the stable environment the oceans provided. Chemical gradients persisted long enough for biological complexity to increase gradually. Ecosystems expanded, eventually producing organisms capable of altering atmospheric gases on global scales. None of that would occur in a world where oceans formed only briefly before evaporating again. The rainfall era turned temporary water into permanent habitat. Even the color of the modern sky owes its existence partly to those early processes. Atmospheric clearing allowed sunlight to interact differently with air molecules, producing the blue scattering seen today. Before oceans stabilized and carbon dioxide declined, such clarity could not exist. The sky itself is a consequence of the rain. The moon's tides, once violently mixing shallow seas, later guided coastal ecosystems. Sediments laid down during early precipitation hardened into rocks, forming future landmasses. Mineral deposits essential to later geological cycles originated from repeated weathering during the ancient storms. The storm era was not just an early chapter, it was the foundation beneath all chapters. When we imagine oceans today, calm horizons, rhythmic waves, we see only the quiet result of a process unimaginably violent at its beginning. Those waters once fell from a sky so thick it nearly crushed the surface. They boiled upon arrival, rose again, and fell once more for ages beyond comprehension. Every drop on modern Earth is part of that inheritance. The world we recognize, rivers, weather, life, exists because the planet endured a time when water refused to remain anywhere except in motion. The storm created the oceans, and the oceans created the possibility of everything else. Once the rains settled into ordinary weather, the consequences of that ancient era continued unfolding across unimaginable stretches of time. The oceans, now permanent and deep, acted as regulators of change. They absorbed heat when the sun grew stronger and released it when the planet cooled. They stored dissolved chemicals delivered by rivers and slowly redistributed them through currents. Every coastline became an interface where rock, water, air, and life interacted continuously. The planet had become self-adjusting. Where early Earth required catastrophic rainfall to remove excess heat, later Earth relied on cycles refined by that very process. Evaporation cooled warm regions. Condensation released heat into the atmosphere. Winds transported that heat elsewhere. Storms no longer existed to reshape the planet, they existed to maintain balance. The ancient storm had evolved into climate control. As continents gradually expanded and collided, mountain ranges rose high above sea level for the first time. Yet even these towering structures depended on water's persistence. Rain eroded peaks into sediment, and rivers carried that sediment to the oceans, forming new landforms over millions of years. Land itself became temporary within a stable system. This constant recycling created fertile environments once complex life appeared. Minerals broken from mountains fed coastal ecosystems. Ocean chemistry remained dynamic but moderated. Life diversified because environments stayed predictable long enough for adaptation. The rainfall era had transformed unpredictability into reliability. Atmospheric composition also continued changing due to biological activity supported by stable oceans. Certain microorganisms released oxygen as a byproduct of capturing sunlight. At first, oxygen reacted with dissolved iron in seawater, forming vast deposits on the ocean floor. Eventually, it accumulated in the atmosphere. Breathable air billions of years later depended on oceans remaining intact long enough for such processes to occur. Without the ancient rain forming those oceans, oxygen would never accumulate. Without oxygen, complex multicellular life would never arise. The chain of cause stretched from boiling raindrops on molten rock to forests and animals in distant ages. Even climate variations such as ice ages relied on oceanic heat storage first established during that formative period. The same water that once prevented freezing later allowed freezing in controlled cycles by distributing energy unevenly across the globe. The planet learned flexibility. Rain continued its ancient journey, ocean to sky to land and back again. But its meaning had changed completely. No longer a destructive force, it became a carrier of nutrients, a sculptor of landscapes, and a regulator of ecosystems. The endless storm became a quiet caretaker. From orbit, modern Earth appears blue because oceans cover most of its surface. That color is a direct visual record of the moment when water stopped returning to the sky and remained below. The blue planet exists because the sky once emptied itself slowly over millions of years. Every wave contains history. Every cloud repeats a process billions of years old. The water cycle we see today is not new. It is the final, refined version of the same mechanism that once cooled a world of fire. The difference is scale and intensity. What was once planetary survival became planetary maintenance, and through that maintenance, complexity flourished. Plants, animals, ecosystems, climates, all layered upon a stable hydrological foundation created long before any organism could witness it. The ancient rain shaped the stage, and everything afterward became the performance. The world did not simply survive the storm, the world was born from it. In the end, the greatest legacy of the ancient rainfall was not the oceans themselves, it was continuity. Before the rains, Earth was a place where nothing lasted. Rock melted, atmosphere boiled, impacts reset progress, and chemistry never had time to advance beyond simplicity. After the rains, the planet entered a new condition. Change still happened, but it happened upon a foundation that remained. Continuity made history possible. Because oceans persisted, reactions accumulated, because temperatures stabilized, fragile systems endured. Because water cycled instead of vanished, the planet kept memory of its past rather than constantly erasing it. Life required that memory. Every organism that would ever evolve depended on environments remaining recognizable across generations. Evolution cannot occur where conditions reset completely each time. The ancient rain transformed Earth from a resetting world into a recording world, a planet capable of preserving outcomes long enough for improvement. That transformation echoes even today. The water you see falling during a modern storm may have evaporated from an ocean, condensed into cloud, frozen within ancient ice, flowed through rock, or circulated through living organisms countless times. The cycle is unbroken, stretching back billions of years to the first condensation from a steam-filled sky. The storm never truly ended. It simply slowed into rhythm. Rivers carve valleys slowly instead of instantly. Waves reshape coastlines gradually instead of violently. Weather changes daily instead of geologically. Yet the mechanism is the same, water moving heat and matter across the surface of a planet that once depended on it for survival. Earth still runs on rain. The difference is that now the rain sustains complexity rather than creating the conditions for it. Forests grow because water cycles predictably. Oceans host ecosystems because temperature remains moderated. Atmosphere stays breathable because chemical balances persist. All of this traces back to a time when the sky itself was an ocean waiting to fall. The millions of years of rainfall were not an introduction, they were the construction phase of a living planet. Every later chapter, from microbial mats to human civilization, stands on that foundation. If the rain had lasted shorter, oceans might remain shallow and unstable. If it had lasted longer, greenhouse gases might never decline enough for diversity. If it had never begun, Earth would be barren rock. Instead, the planet found balance through persistence, and so the quiet rain we hear today carries an ancient meaning. Each drop repeats a process older than life itself, a reminder that the world was shaped not only by fire and impact, but by patience measured in millions of years. The storm did not just fill the oceans, it created a world capable of remembering, evolving, and eventually understanding its own origin. The world we inhabit is not merely a planet with water. It is a planet built by rain.